Now, statics. So far, we've mostly been looking at dynamics where there is an unbalanced force and there's an acceleration equal to ma. And you have to figure out combining the forces that are resolved along the incline, friction, tension, whatever it might be. Also, I'm jumping ahead. You don't need to frantically find this page, but I'm also trusting that you watched the lesson from Thursday, which involved a couple of fun things. Miss Owen, when she worked in that tall building in the city, went and took the set of scales and filmed the normal force of the scales. Fun story about that elevator. It was accelerating too fast, and so the normal force was so large that some people were known to have like fallen over or stumbled inside the elevator. Little old grandma comes in to see grandson at the Rio Tinto Tower and couldn't handle that massive acceleration, so they actually had to dial it back. But it turns out if you want to get to the top story of that building, you're traveling, something around 30 or 40 kilometers per hour. So the acceleration was occurring for about 5, 6, 7, or 8 seconds. Pretty crazy. Did you watch that video?
Yes.
On the YouTube? All right, cool. So just be aware, in the vertical, we can resolve our forces again. As long as you write this out, and as long as you assign your sign convention, you can't really go wrong. Okay? So every question, make sure you write this out. The sum of all forces produces an acceleration. It's caused by two forces in this scenario, and we'll assign that gravity is negative and normal force is upwards. Then you're just picking it apart. Providing you include the direction, you're always going to be good. Okay, let's now go to statics. This might be a little bit leading into the Year 12 course, but it's not that tricky. Basically, when an object's in equilibrium, we can make this statement that all of the forces balanced are equal to 0, but we can also say that all of the forces in the horizontal sum to 0, which means that the acceleration in the horizontal is 0. It's not accelerating left or right. In the vertical, the same. It's not accelerating up or down. We call this translational equilibrium. Okay? It's not translating left, right, up, down, forwards, backwards. We need to include our sign convention. Okay? So whatever you decide is up, whatever you decide is down, whatever you decide to the right and to the left, you must stick with that convention. And ideally, I'd like you to use that convention that is used above. Let's consider a mass of 5 kilograms that is suspended by a rope that produces an angle. So essentially, we can say there's a rope going this way. We'll call that T2. And a rope going that way, we'll call that T1. And they're making an angle. Now, ignore the fact that the ropes are at the end. We had a mass over there by the wall. It was just being suspended by a rope, and where the hook was, it pulled down. Essentially, it created two different tensions. Okay? Now, I've drawn in two of the forces. We've got tension, and we've also got the weight force down. All right, so I'll just write that as Fg equals 49.0 newtons. Now, sometimes you might be asked to draw a free body diagram, which is simply an object drawn as a box, and the forces travel away from the center. All right. Fg, weight, however you want to call it. So that's your free body diagram. A vector diagram is where you draw it tail to top. Now, since this object is in equilibrium, when I draw these forces in, they're going to complete and return back to 0. There's going to be no resultant. So we're basically completing the triangle. Now, drawing this vector diagram, we can actually solve using very simple geometry. Unfortunately, we need to use the method that Wace wants, but let's just look at the geometry first. Well, I've got my angle up here as 20 and down here as 20. I could draw in a baseline to the horizontal here and go, well, that's 20 and that's 20. And so the total internal angle must be 40. Now, in this example, it is perfectly scalene that T1's magnitude will be equal to T2's magnitude, in which case we can just use the sine rule and you can solve for your tension. However, we want to actually use the correct working out. We're going to look at these forces in the horizontal. I'm going to call this T2x, and this one over here is T1x, in which case we can solve, let me just color code this, that the horizontals sum to 0. So let's just do the y ones first. Let's draw in the vertical component of each of the tensions, T2y and T1y. And here are the verticals. So I'm just going to highlight my vertical components. Oh, I've got one there as well. So what we're seeing here is that the vertical components of the tension must be equal and opposite to the weight force. Okay? So that's why we've got to split these guys up. This is a very essential skill. You've got to pick your vectors apart, play around with them in the vertical, play around with them in the horizontal, and then recombine if necessary. There will always be a mark. As you saw, you write the following: sum of all forces in the y. In this case, you can just write equals 0. We don't have to include Newton's second law. And then that's going to be produced by T1y plus T2y plus gravity. Now, I've already assigned my convention, but I'm going to say that those two are positive and the weight force is negative. So let's now write it as 0 equals, well, that's going to be T1 sine theta, or sine 20, doesn't matter, T1 sine 20 plus T2 sine 20 plus negative 49.
Should you say that T1 and T2 are equal?
Well, we have to make that assumption. There is a wild assumption now. We have to say that the magnitude of T1 equals the magnitude of T2. And so now we can say, well, we've got 2 T sine 20. We're making an assumption here. They have to be. They can't be any else. To make equal angles, their side lengths must be equal.
Well, there's not a lot of information here. It says a rope as well.
Mm.
And the question actually says a singular rope.
Yeah, but by suspending the... Do you remember the hanging mass on the string over there? So that's kind of what we've got. All right, rearranging for t, I'm going to say t equals 49 over 2 sine 20. And the calculator spits out that for this to be in equilibrium, the tension must be 71.6. Now, let me just color code. My verticals were blue. Oh, that should have been a highlighter. Come on, laptop. There we are. Let's just quickly check, and this should be pretty self-explanatory. Let's just check the horizontals. And that is that the sum of forces in the x should also sum to 0. Well, that's going to be equal to T1x plus T2x. We now remember our sign convention. I'm saying that T2 is acting to the right, which is positive in the x value. T1 is acting left in the x value. So let's just quickly check. Does that equal 0? Well, 0 equals negative 71.6 cos 20 plus 71.6 cos 20. Well, they're equal and opposite. All right, so that's the maths there that says that the horizontal forces must be equal and opposite because this object is in translational equilibrium. Let's go to a question that's a little bit trickier. So, and we shouldn't have to make any assumptions for this.
You didn't have to. If you started with the x, you could have done that they're equal, and then done the y.
You could have shown that, but you get that T1 equals negative T2.
Why would you get that?
No. The T1x.
If you rearrange this equation, Emil,
You can just add in the sign.
if you use that equation, T1x equals negative T2x. But then if you take that into the vertical, you can't take the sign convention. So at most you could say the magnitudes are equal. And then when you go into the vertical, you then force a separate sign convention. So the maths does kind of break down when you go from x to y.
Oh, okay.
Okay? All right. Cruising along. That term, I told you right at the start, that is telling us a lot of stuff. It's telling us that it is in translational equilibrium. We don't care what speed. We don't care how fast. We just say that all of the forces acting must be balanced. Let's just draw a very simple. You're going to have your force down, Fg. You've got your tension, which we said was 300 at an angle of 45. You've got a frictional force backwards, which we're not sure of. And we've also got a buoyant force. Now this is new. We haven't really looked at a buoyant force, but you're displacing a certain value of water. So there must be an upwards force. So let me just finish this off just for the sake of, let's highlight the horizontals. All right, so the forward component, the horizontal component of tension, which I will write underneath as T cos theta, must be equal and opposite to the friction force. And the vertical component Ty, which is T sine theta, well, we've got a few different components now. We've got 3 components. Before we solve, let's just get familiar with our free body diagram. We've got weight down, we've got our tension that way, we've got a buoyant force upwards, and we've got a friction force backwards. Okay. Now this is getting a bit trickier now. Instead of just 3 vectors that make a triangle, we've got 4 vectors, but it should now complete the square, complete the quadrilateral. So it doesn't matter how I draw them. Remember, the order of operation of combining our vectors does not matter the order that you combine them. They should complete the square because we're in equilibrium. Well, maybe you could do a little bit of, slicing your shapes into triangles and rectangles, but really what we need to do is write our statements out. Sometimes you have to do it one way then the other, but it turns out in this example, it doesn't matter which one you start with, horizontal or vertical. You can solve, I should write that as Tx. But remember, convention. So I'm going to assign that friction is negative, tension is positive, and we are summing the pinky boys. Well, we would say 0 equals FF plus 300 cos 45. So FF must be equal and opposite to that. Calculator says that the horizontal component of tension is 212, and so friction must be equal and opposite to that. Well, let's just say left. Not leaving myself much room, so apologies there. Now let's solve for the verticals. Sum of forces in the y equals 0. Having a look at that diagram, we've got 3 vertical components. Doesn't really matter what order we write them in. FB plus FG plus TY. Now with this sign convention, our buoyant force is positive, gravity is negative, tension is positive. So, we write them out. 0 equals FB, that's also an unknown, plus, well, we didn't solve for it, I'm going to write it here, 60 by negative 9.8. Hang on, let me just remember color coding the negative. Plus 300 sine 45. That's enough. That's your intermediate step. This is your second mark of the 3-mark question. You can just jump straight into FB. It's going to be plus 600, take 300 sine 45. Calculator spits out plus 376 newtons. Okay. It will only be that measurement for those values given. If we changed friction, if friction was too big, he would start slowing down. If friction was too small, he would speed up. If the buoyant force was less, he would be sinking into the water. If the buoyant force was more, he would be rising out of the water. But we were told cruising along at a constant speed. Okay? Okay, now you try. I will give you 10 minutes, 5 minutes, I haven't decided, to do exactly the same thing. In fact, the end of the lesson. We've only got about 6 minutes left. So, it's exactly the same, but instead of the buoyant force, now it's the normal force.
These aren't really questions, sir.
Solve for FF and FN.
I don't know what to solve for.
You just said.
But
again, it doesn't matter which one you solve first, you can solve them independently.
I just realised. Can you just scroll off? I think you might have put sine twice.
No,
Oh no, you put cosine there.
cosine, cosine.
My bad.
Draw a vector diagram. This time you might like to add them in a different order. Oh, don't do. Oh, yeah. There's a,
so what's the answer?
I don't know. Which one?
The normal force.
54.7.
And then friction.
25 even. So, sum of forces in the x equals 0 equals FF plus TX. What was T? T was 50. $60 sine? 50. 50 sine 60?
60 sine 50.
50 sine 60. Yes. All right. Who would like, in the last 3 minutes, to have a go at the next question? I will give you a hint. Well, maybe I won't. No, I'll give you a hint. You have to solve
Why?
T2. Well, let's just draw in FG, T1, T2. If I highlighted the horizontals, you will see that there are two unknowns. But if I highlight the verticals, you will see that there is only one unknown. So I would say
So they're not in equilibrium yet.
they are held in place.
Oh, okay.
But in this case, we know we can make a statement for the x's, but you've got two unknowns. Let's find T2 first by summing the verticals to 0. Sum the verticals to 0, find T2, and then put T2 into the horizontals. All right. I'll draw in the free body diagrams later. Let's just quickly get this bad boy done.
So we don't ever have to do the vector diagrams, do we?
You might be asked to, yeah.
That's a no then. Should we do 3 sig figs? Or?
Yeah, 3 6 figs.
Let's do.
Correct. Ooh, that green is sharp.
Right, how do you do this?
So we solve for T2. I found the magnitude of T2. Now I can use it to solve the 0. Now this one's going to be T1 plus T2 cos 50. Okay. All right, and that is time. As you are departing, I'll just complete your free body diagram. Pretty damn easy.
So did you sine 50 or sine 40?
50.
Yeah, it should be 40.
Nope. Disagree.
Oh, that is.
Fight me tomorrow. I've got cross-country training.
What are you doing across country training?
5 by 1k intervals, and then we might run to that hill between the train line and the top of Stirling Highway Hill. There's, you know, those two roads that run parallel, and there's that parky bit in the middle with
I
the
live on that street.
the footpath.
Grand Street.
No. No. Do you live near Gawa,
Yeah, where?
the Gemstone Association of Western Australia?
Where's that?
Well, Grand Street. No, wait. Hang on, I'm still screen recording. Let's continue.